Welcome everybody to this week's Geometry and Topology seminar. This week's speaker is Brendan Guilfoyle from Munster Technological University, who's going to tell us about umbilic index points and holomorphic disks.
Thank you very much. It's nice to be here again. So I'm going to talk about, as I said, umbilic index points. I think it's a while since I have talked about this topic. It's actually old work, but it's kind of taken a long time to finally appear in print. And then some new additions onto it, which hopefully you'll find interesting. So in particular, let me go to the start. And this is what I want to try and explain. So this is and it is, as I said, about umbilic points. So the umbilic, or the index, sorry, let me just say, so the index of isolated umbilic point on a. Now there are some technical details that we'll need to put in. I will as I go through. There's a lot of different aspects of the problem that kind of call upon different techniques. But I'll just talk about C3 plus alpha. I won't really discuss about smooth. So these are Holder spaces. So on a C3 plus alpha smooth surface, the technical requirement is less than 2. So the index, if we call the index I, we're just little I. We'll have more than one index as we go through this, so little I may as well introduce it. Now is the umbilic index. So what do we mean? Of course, classical differential geometry. I guess just very briefly for definitions, and these are things that would be fairly standard. So an umbilic point on a surface, so let me call the surface S from the get-go. So an isolated umbilic, so what do we mean by umbilic? So an umbilic point, umbilic point on the surface is a point where two curvatures, or two principal curvatures are equal. So it's like a round point in some sense. Principal curvatures are equal. So equal, and then our index. So the index of an isolated umbilic point, of course, the umbilic points will be singularities of the principal foliation. So you have a foliation of the of your surface, and you'll have a singularity, and at that point, then you'll have a winding number. So the index here, and I should mention that this index is actually a half integer in general. So because it doesn't have to be orientable, it just defines a line field on the surface rather than a vector field. So the index is the winding number. So the winding number of the lines of curvature, or principal foliation is another foliation about okay, so again, very standard, but good to just at least put them there for once. So again, definition for what we mean by the index. We call this the umbilic index. We will have other indices that will appear at various stages. To compare, just as a comparison, because of course these are very old questions going back a long time, about the Cartesian conjecture about whether a closed surface must have two umbilic points on it, and that actually follows from this. And the other one, I guess, is this is Hamburger to compare 1941, I think it was, the papers around that time, which states that. Let me just say briefly, on a real analytic surface, it's stronger. Surface, this I must be less than or equal to 1. Okay, so being less than 2 and less than or equal to 1, of course, the gap will be 3/2, of course, because it's a half integer. Now, in describing this, there's a number of different elements that have come into the proof, so we're going to talk about a few other things first before we come back to the specifics of how we go about to proving this. So we have geometric setting and the background that we're going to be discussing. So again, many of you will be familiar with this from previous talks, but let me very briefly describe. So L is going to be the space of oriented affine lines. So oriented affine lines in R3. So not the projective lines, we're just talking about space of lines, oriented lines in R3. And you can describe that by two vectors. If you were to do a picture, there's your oriented line, there's your origin. You can, of course, take the perpendicular vector to the origin, let's call that V, and let's take the direction U, and so it's going to be U, comma V, both vectors in R3, which satisfy two conditions, U dotted with V is 0, and the length of U is 1. Okay, so that's two conditions on 6 variables, so it's a 4 manifold, and in fact, it's the total space of the tangent space to S2. So it's the tangent bundle of S2, and you can see it very, very easily by taking this unit vector and just parallel translate it to the origin. So that's your U, and then it's on the unit sphere because it's a unit vector, and then if you parallel translate this down, this is perpendicular, so you can see what you're getting is V is actually okay. So that's the identification of the space of oriented lines with TS2. So sometimes I write down TS2 off the top of my head, and sometimes I write L, depends. But again, they're the same thing. Now, there are lots of canonical structures on this manifold, 4 manifold, and they have particular relevance to R3. So the first thing, of course, is a projection. You have a natural projection from this bundle. So pi, which takes TS2 to S2. That's the simplest one. So that takes every oriented line and gives you its direction. The next is a symplectic structure. Now, there are many ways in which I can motivate these. There's a trio of structures that we're going to be talking about, and you can define them in lots of different ways. The simplest way here, the way I'm going to do it now, is just to take the round metric and round metric. You think of the round metric as taking TS2 to its dual, to its cotangent bundle S2, and then you can take the canonical symplectic form on the cotangent bundle. You have that on every cotangent bundle. So you have omega canonical, and then you can pull it back with this round metric. So G star, and that will give you a symplectic form on TS2. So that's just a natural way to pull back from the cotangent bundle to the tangent bundle, gives you this symplectic form. So it's a 2 form, non-degenerate 2 form.
Excuse me,
closed.
Before you erase this index, I mean,
yeah.
I'm a bit puzzled. Could you give a drawing?
Oh,
to
sure.
see how
So sure, yeah. So again, what you have to look at is the principal foliation on the surface.
Yeah.
And so if your surface, for example, was rotationally symmetric, so if you had a rotationally symmetric surface, I'll draw a flat foot, say some kind of ellipsoid, the rotationally symmetric ellipsoid. Well, then you'd have your umbilic point, your principal foliation, which would be actually a pair of foliations which are orthogonal, so you can take either one, would look like that. And so there your winding number is 1. Right? So this is the index is 1. If you take the non-rotationally symmetric ellipsoid is kind of the standard one to take. If you draw it has 4 umbilic points, each of index 1/2, and the foliation looks like this, and then a similar one in the other direction. Right? As a famous picture, I think Jacobi discovered it. And if you look at this as you go around, this is a non-orientable one. You come back with the line twisted, or at least flipped over. So that's a 1/2, 1/2, 1/2. Of course, rotationally symmetric surface, you'd have a 1 and 1. So obviously you have the other characteristic of the sphere. If it's a spherical sphere you're talking about, they'll all add up to 2. Okay? So 1 + 1 or 4 1/2. Okay? So that's that's the typical kind of examples that you could construct very easily for this index. These are the umbilic points, and that's the winding numbers if you compute it.
And you said quickly that was this the Kara-Theodori conjecture? And
yes,
how
so
it follows?
that's a global one. So the global one says that the global Kara-Theodori conjecture says that if you have a closed convex surface, it must have at least 2 umbilic points.
Mm-hmm.
You know it must have at least one because the Euler characteristic is 2. So theoretically, you could have a closed convex surface with a single umbilic point, and its index of necessity would be 2.
Yeah.
Okay, so that's we exclude that by saying no, the index has to be less than 2.
Yeah. No, it's okay.
So that follows from that.
But could there be an index we have for S3 plus alpha?
3 over 2?
Yeah, could there at least one?
Yeah, so that's a question. No one has seen a 3 over 2.
So it's still possible.
Okay, so what I would say is that the gap between this first statement of the theorem that I'm going to be talking about and Hamburger suggests that you should have a 3 over 2, but it won't be real analytic. So this may be the difference between real analytic surfaces and smooth surfaces. Okay, which is a very complicated and very little, it's not very well understood really that those two different categories for surfaces. Right? So yes, it does suggest, and okay, so what I will show you, it's kind of a topological kind of argument that gives you this local index bound, and you kind of see that it exhausts it. So it does suggest there should be 3 over 2s, right? So in the spirit of the theorem that I state, you should have smooth 3 over 2 umbilics, but no one has ever seen them, and actually most people would have thought that they didn't exist, in fact, because of that. I guess most people have tried to prove Hamburger works even in the smooth case, which again would rule out the 3 over 2. However, that's not the. Anyway, our result suggests that that's not true, that you could have a 3 over 2, but it's smooth and not real analytic. Okay, and this is why it's kind of a mysterious beast. If you could find one, it would certainly shake things up a bit. You could write one down explicitly. So we have two canonical structures here. Well, we have objection and we have the symplectic structure. Geometrically, we also have a complex structure. So initially, I'll write it down. It's an almost complex structure. So for a complex structure, we have to take, say, a vector in the tangent space to TS2, where gamma is a line. I'll use gamma to represent a line. And of course, the typical way to represent an infinitesimal variation of a line, which would be a vector field, a vector as we're talking about here, is you take your oriented line and then you'd have your Jacobi field, which would be an orthogonal. So this is kind of what your x would be. X was a Jacobi field. For an infinitesimal variation, it has to be linear, so it has 4 parameters. And, that's the tangent space at that place. Okay, and then J of x at this point, gamma, is rotation. Rotate the Jacobi, rotation of the Jacobi field, through 90 degrees about your line gamma. Okay, so that gives you, well, a priori, that just gives you, so you just rotate the Jacobi field, and it turns out that gives you another Jacobi field, so you have a map on Jacobi fields, which takes x, right, that preserves the tangent space. It squares up to -1, so it's an almost complex structure, and it turns out because we're working in a flat space, it would actually work even if it was any constant curvature 3 space. You can define this J and it's integral, right? So it's not just an almost complex structure, it is an actual full proper complex structure. So that's it's also compatible with the symplectic structure. So if you omega JJ, you just get the same as omega, and then of course you can put the two together and we'll get a metric. And so the metric, let's say G, capital G, that is just omega with the J filled in here. So that's our metric. So it turns out that this metric is, so let me just state, this is maybe so 5. So that these three together give you a Kähler structure on the space of oriented lines. So this is a Kähler structure. In fact, it's a pseudo-Kähler structure. So it turns out this metric is not positive definite. So let's say omega, J, and G are let's call it a pseudo-Kähler structure on L. And in fact, a little bit more, I'll say, and G is of signature 2,2. So this is one of the weird things that happens, and unfortunately it's unavoidable, but it's not a definite metric. If it was a definite metric, I think we'd be living in a very different world. But it's an indefinite metric, and its signature is 2,2. So it's These are not studied very much in geometry, come up in some cases, but here's one I certainly think it's interesting. It turns out it's conformally flat and scalar flat, but it's not flat. It's not Einstein's not flat and scalar flat. It has curvature. It has Ricci curvature, has non-zero Ricci curvature. Even though we're working, this is on the space of oriented geodesics are of a flat space. In fact, this metric is not flat. Okay. So the other thing, and this is probably the reason why it's going to play such a big role, at least parts will play such a big role, I'm going to talk about it, is that if you look at the Euclidean group acting on R3, it of course maps lines to lines and therefore gets an induced map on L on the space of all lines. And so, in fact, this metric is invariant under that. So, in fact, all of them is invariant under the Euclidean action. Under the Euclidean action. Euclidean group. Euclidean group acting on L. Okay, so what that means is that many of the problems in Euclidean space can actually just be all transferred over into the space of oriented lines, and there's no geometric loss. If you can formulate it there, you can formulate many, many problems from R3 into the space of oriented lines naturally, and the Euclidean geometry will be transferred over into this strange, it's a higher dimensional space, you know, it's four-dimensional space, it has a weird signature metric, but somehow the geometries of the two are very closely linked.
Is it homogeneous, right? It's homogeneous because you can map every oriented line into another.
Yeah, every line.
So the curvature should be constant.
No, it's not constant curvature now.
No, I mean, so the curvature should be determined by at one point where it is, right?
Okay. Yeah.
And what is the Ricci curvature there? Does it have different signs? Are both signs positive and negative?
The Ricci tensor has both signs, yeah.
Mm.
In fact, talking about the sign of the curvature of a 2-2 metric is already a little bit, you know, you'd have to do a bit more work to it's not quite as straightforward as saying positive curvature or negative curvature in the case of Riemannian. In fact, you can of course flip the sign of everything here as well. The metric with the minus, just let the 2-2 go in the other direction. So yeah, it is hard to, I guess that's one of the reasons perhaps that 2-2 metrics are not so studied, is because a lot of the paradigms that you use in the Riemannian case simply don't work. Like positive curvature being associated with things closing up, and negative curvature with things opening out. And those kind of things just don't quite have the same impact. The other thing is, of course, it doesn't lead to elliptic problems in many ways because of this indefinite signature. It leads to ultra-hyperbolic problems. So you don't have a lot of the stuff that you would have with definite problems, elliptic problems. You tend to get these kind of weird hyperbolic problems coming out of this. Now, of course, it must be said that, you know, even in Euclidean geometry, if you look at things like rigidity of shells, there are hyperbolic problems that naturally arise in Euclidean space. And in fact, in many of those, it's because of this 2-2 metric. You can trace it back to this metric. So that's also something that we can. Okay, so let me just now, one way that I guess you could also see this whole picture, and I'll put something here now. If you just take R3 and you look at the unit tangent bundle, so that's just S2 cross R3, or 3 cross S2 if you like, and if you quotient out with the geodesic action, you just get TS2 or L. So it's the same thing. Right? So if you identify two vectors or 2 points of vectors on two different places, if they point in the same direction and there's a line joining them and you identify them, it kills exactly one dimension from this 5-dimensional space, and you get this TS2 constructed in that manner. Okay, so this is sometimes called the mini-twistor correspondence. It's useful in some ways if you take a point in TS2 and pull it back with the inverse of this map and then project it down, you get a straight line. And if you go the other way, if you take a point here and you pull it up to here, you get a sphere, and then you project it down into here, you get a sphere, the sphere of lines through the point. So this correspondence space allows you to go from subsets of here to subsets here and vice versa. That's a correspondence rather than a map. So in particular, let me just draw out how this geometry, and again, all of these different aspects of it are all, I think, are interesting in their own right. And so, of course, as I've just said, if you take an oriented line here, then this is a point in the space of oriented lines, of course. That's our standard definition here. On the other hand, if you take a point here, you get a sphere of lines here, naturally, which is, again, just by tracing up over that correspondence space. So from point to spheres line. If you take a surface here, And here we see a little bit more of the naturality of this whole setup and the way geometrically they're fit together. The surface here, S, if you look at its normal lines, you get a surface of normal lines, surface of normals. And this is another surface then in the space of oriented lines, and in fact it's Lagrangian. So again, if and only if you have a Lagrangian surface, then in fact there's a surface in R3 orthogonal to the set of lines. So it's like Frobenius theorem takes you back and forward between those two. Let me just see the order I'm going to put these in. On the other hand, what we've been talking about here is a convex. So if you have a convex surface, well, if it's convex, then you can parameterize it by its Gauss map. That means your oriented lines can be parameterized by the base, the S2. So in fact, this means you have a Lagrangian section of your canonical projection, I said earlier, Lagrangian section of your pi going from TS2 back down to S2. The other point, and this is where things start getting closer to what I'm going to be talking about, is umbilic points. So if you have P as an umbilic point, so you have your surface and you have your point P on it, that's umbilic, and you look at the oriented line, that's gamma, well then this point gamma is a complex point. It's a complex point on your Lagrangian surface. Now, a complex point, what do we mean by a complex point? Well, you have your J operating on the ambient space, and if you take the tangent space to your surface, you apply J to it. Generically, you'll get some other tangent, another plane, and this plane, if it is the same as the original plane, if the J preserves the tangent space, we call it a complex point. So if the whole thing is all complex points, well, it's exactly a complex curve in the normal sense of the word. But you can have it just at a point. So complex points, more than that, in fact, your index, so your index of your, so again, we'll have a few, so let me just, the umbilic index I gives rise to the complex index. So again, isolated complex points on a surface in a complex manifold complex point have a well-defined index, complex index. So I'll use capital I for that. And it has to be a whole number, so it turns out to be just twice the other one. All right, so you have a notion of umbilic index and you have a notion of complex index in this four manifold, and they're the same mod, just multiplied by 2. You could also look at, say, the lines of curvature. We've talked about this foliation. So the lines of curvature here, well, it turns out that this Lagrangian surface in this setting is going to be hyperbolic. The induced metric has signature 1, 1 generically. And so these are null curves on this base. So your sigma is a Lorentz surface and it has null directions, and null directions are precisely the lines of curvature. So again, you see that what you find is these definite geometric constructions all have these indefinite reinterpretations, equivalents. And I could continue. A Weingarten surface is one that's flat, etc., etc. So you can go up to higher derivatives and you still get this geometric, translation between problems in R3 or geometric things in R3 and in this four-dimensional space TS2. Okay, so that immediately says that, and again, it's not going to work for all geometric problems in R3, but certainly we can restate the first theorem that I wrote down. All in terms of TS2, it's completely equivalent. And it's in that space that we're really going to go about trying to solve it. Okay, so this is the same theorem as I wrote down the first time. Okay, so the complex index of an isolated complex point on a Lagrangian, that means that it comes from a surface in R3, section, because it's convex, satisfies I must be less than 4. It's exactly the same statement, except now transferred over into this rather different geometric setting. So the complex index can be captured or at least described in that setting.
And you had something that was analogous to your C3 plus alpha as well.
Excuse jet, I should say. Yeah, C2 plus alpha because we're in the one jet. Yeah, so the way I tend to think of TS2 is just kind of the one jet, you know, it's you're just looking at the space of derivatives, geometrized so it's slightly smaller than you would expect. So yeah, so Elegron is C2 alpha. C2 alpha. We'll do a few. Yeah, thank you. Okay, so now, what is the advantage? Of course, transferring into a bigger space, of course, is not exactly new in mathematics. Sometimes extra space gives you extra, you know, room to move around. So let me now pose a problem in this four manifold, which has important implications for solving this problem, proving this theorem. Okay, so this is what's called the Riemann-Hilbert problem. So there are many different Riemann-Hilbert problems, so let me write this. So Riemann. So this is where the second part, if you like, of the title, where the holomorphic disks come in. So Riemann-Hilbert problem in L. So the idea is, I'll just state it as a kind of a problem, and then I'll give you some results that, so given a surface, we'll just start with any surface initially, but some restrictions eventually. The idea is find a map F which goes from the disk, these are the two disks, just the standard two disk, and its boundary, and maps it into this four manifold, and you want the boundary to lie on this surface, and you want it to be holomorphic. So del bar F, you want to be 0. Scratch this complex structure. Okay, so this is, well, if your surface doesn't, away from complex points, so this is an elliptic boundary value problem. Boundary. Now it only refers really to the complex structure, there's nothing else really there, we don't need a metric or anything like this, so even an almost complex structure will do. This is an elliptic boundary value problem. And it has another index, the analytic index. I won't give it the specific name just because it's I don't need it specifically with analytic index. So again, if you know.
What is D again? What is D again? Here is it a disk?
Sorry?
Is a disk. Is a four-dimensional disk?
Oh, two-dimensional disk.
Two-dimensional
Yeah,
disk.
sorry. I just wrote D. I could have wrote D too. But
okay.
So it's just a two-dimensional disk. So we're looking for a disk that sits in this, which is holomorphic, sits in this four-dimensional space, and its boundary lies on this surface. Okay. Generically, they would not intersect. Well, they'd intersect in a point, but you actually want the whole curve of the boundary to lie in it. So it's a non-trivial condition. Now, of course, if you like this from standard elliptic co-kernel of your del bar operator. Now, really, you're working with the linearization. You have a solution and you look at the linearization, etc., as you normally do with elliptic problems. But you get this index, and this index, analytic index, difference between the dimension of the kernel and the co-kernel. And this is a standard result known that this, in this particular setting, is the Maslov class of boundary plus 2. So mu is Keller-Maslov. So, mu equals the Keller-Maslov. So it's really a function of mu of the boundary. It's a little bit more than that. Maslov class of the boundary. And in fact, it's a relative first Chern class. It's also, you can express it in terms as a relative first Chern class. Now, if the boundary of D bounds a disk on the boundary surface. Now, a priori in this setting, I haven't said anything about the topology of this surface. Generally, it's going to be a sphere, or it's just going to be a disk itself. But if the boundary of the holomorphic disk bounds, so you have your picture, you have your sigma in this four manifold, and then you have a holomorphic disk that you want to attach to it, and this is the disk here that's in there. Okay, so if the boundary bounds a disk on the surface, then in fact this Maslov class of boundary is actually just twice the sum Yeah, well, I'll just call it capital I. It just means the sum of the complex indices of the points inside. So if you have complex points inside there, then they have each of them has a complex index, and if you add them all up, multiply by 2, that's the boundary. That's the Maslow class of boundary. So it counts how many umbilic points, or how many complex points, I should say, in the set, how many complex points are inside the boundary curve, if there's a disk in the interior, that is. Okay, in fact, let me just, when we come for the Riemann-Hilbert problem, for these elliptic boundary value problems, of course, what we really want to look at is the dimension of the kernel of del bar. We don't want to have the co-kernel. We'd like to get rid of the co-kernel generally, so it's less geometrically interesting or less quite difficult to work out, in fact, whereas this would be the space, the dimension of the space of holomorphic disks that satisfy this boundary condition. So again, the technical condition we need for there, so if the problem is what's called Fredholm regular, is Fredholm regular, then let me write down this dimension of this kernel, of the kernel of del bar operator, then is going to be, well, it's the twice this total index as we're just adding up all the indices, plus 2. Now I will say, so the co-kernel is 0, so essentially the Fredholm regular just means you can perturb your surface a little bit, your boundary value problem a little bit, and you'll end up killing the co-kernel, get rid of it. It's all to do with these Banach space kind of setting that you set this whole thing up. Here, this is, I should say, for parameterized disks. So here, parameterized disks. And of course, you can reparameterize disks, and there's a Mobius family. So in fact, there's 3 dimensions of Mobius family. So if you want to go to unparameterized disks, in fact, if you like, I'll say the dimension of the kernel of del bar is going to be 2i minus 1 if you subtract off the freedom that you have from this 3-parameter family Mobius transformations. So that's when we're talking about unparameterized. That's really the space. That's really the parameter. When you're unparameterized, you can. It's going to be 2i minus 1. Okay, so now let me. So a little bit of functional analysis there for the. Again, essentially, it's Sard-Smale is the key tool for this kind of general setting. Okay, so then let me call this theorem A. It's going to be referring to this again later. So theorem A, so again, this is myself and Wilhelm recently, 2020. So it's defined, so let sigma be a closed surface. Well, again, we should put in actually C2 alpha is probably enough, but anyway, I'll say C3 alpha, probably get a bit sharper, surface in L with a single umbilic point, or a single complex point, I should say, single complex point. Then the Riemann-Hilbert problem is Fredholm regular. Hilbert problem is Fredholm regular. So it has this nice property that we want over there. How do we do this? Well, essentially the Riemann-Hilbert problem goes bad at complex points. You want a totally real boundary condition for these holomorphic disks, because if it intersects on a complex point, it's then going to end up actually being tangent, so it's no longer transversal. So complex points in general on these boundary surfaces are not good for finding holomorphic disks. However, if you have just one and you have enough symmetry in the space, then you can quotient out in a way and you still get Fredholm regularity. So the main thing here, element of the proof, is this fact that the isometry group of this whole setting is the same as the isometry group of R3, which is quite big. It has enough elements to fix a point. Right? And so when you fix a point, you can kind of kill the variations, and then you can go through some of the standard machinery and it all works well. But you can only do it 1 point. The group is not big enough to fix 2 points. Okay, so this is why 1 point is no good on one of these surfaces, right? Because the group, it's the size of this, of the isometry group. So let me also point out that, again, just to see why this is, if you take the flat metric in R3 and you perturb it a little bit, then the Carathédroid conjecture is no longer true. So I've constructed metrics without symmetries. So again, just to highlight the role of symmetry at this point, you can look at metrics on R3 and you can find ones that are arbitrarily close to being Euclidean, and you still have counterexamples to both the local index theorem and to the global one. So you can find closed surfaces with a single umbilic point, and you can also find surfaces with umbilic points with arbitrary index, right, without any index bound. So again, the role of symmetry here is the reason why this, if you like, if you want to think, why is Carathédroid true? Why is it, well, you can get these things very close together. Why can't you get them exactly together, these two umbilic points? And the answer is, well, it's the symmetry in the background here. If you were to do that, it would be Fredholm regular, as we'll see. Okay, so that's use the isometry group, and I'll say this symmetry group breaking means that this is no longer true if you were to get rid of this high degree of symmetry that you have in the situation. It also suggests that the same degree of symmetry for constant curvature spaces holds, and that these conjectures actually do hold in H3 and S3 as well. Okay, which I think is also, that has been known that they're equivalent. But again, it's the high degree of symmetry in these spaces that allows, that introduces this obstruction, if you like, to having umbilics of any index and any number of them on the sphere. Okay, so the other theorem, so this is the theorem B, which is to run counter to that in some sense. So theorem B says, so again, this is more recently, itself in 2024. So this says, so again, let me write it down, that sigma L via, so when I say totally real, I just mean it has no complex points. So a surface with no complex points is often referred to as totally real. So it's a totally real, it's Lagrangian, and it's a hemisphere. So by a hemisphere, I mean that if you take pi of it, so pi here was this projection, the first construction onto S2, that this actually is a hemisphere in S2. Hemisphere. So pi here is your projection from TS2 down to S2. So let sigma be a totally real Lagrangian hemisphere, then there always exists a holomorphic disk with boundary line, holomorphic disk with boundary line on sigma. So this runs contrary to watch out. So if you have a totally real surface, you have this Lagrangian hemisphere, it's totally real, has no umbilic points, and then you try and attach a holomorphic disk, well, there's no complex points in it. So therefore, the dimension of the kernel should be -1, right? Because, right? And when you have that, then you expect any perturbation in the if there is a holomorphic disk, it'll disappear. The space of holomorphic disks has negative index, so actually you won't have any holomorphic disks, right? So this means that you cannot take a surface like this because of A and B, because of the comparison of these, you cannot take this and complete it forming only one umbilic point, right? Because then it would be Fredholm regular and those disks wouldn't exist anymore. Okay? So the question of taking a totally real hemisphere, closing it up, you can, as you close it up, you're going to create at least 2 umbilic points. You can't just create 1 umbilic point because then it would have been Fredholm regular and those disks wouldn't have existed in the first place. So in fact, if you like comparison, so theorems A and B, prove the Carathédroid conjecture. Prove this Carathédroid conjecture where you must have at least 2 umbilic points on a surface, a closed convex surface in R3 conjecture. Okay, in fact, it also proves another conjecture of Toponogov about complete planes, umbilic planes in R3 must have at least 1 umbilic point, albeit at infinity. So in fact, it's the same more or less the same proof actually works for both this and this conjecture of Tokunagawa. Okay, this is the global thing. So what about the local, right? So let's go back to that original thing about the index. So what I want to show you now is how you can actually leverage this, everything I've said here, and you can extend it to this local index bound. Okay, and this is more constructive in some sense than what I've just done there. So, we talk about the local index bound. And you'll see that it has more of a kind of different flavor. Okay, so again, it's a proof by contradiction. So it's this theorem A and B are going to be the main contradiction. But the problem is you start out with a surface. So again, let S be a surface. Convex again, so satisfying all of the things I said earlier. Convex surface with isolated umbilic of index. Well, let's take I to be 2 plus k over 2 for k greater than or equal to 0. K equal to 0 will be the Carathéodory, but now we're going a little further. We're going to show that you can't get any, even on an open set, you can't get it. Okay, so suppose you have such a surface. So again, it's just going to be a small disk, and then you'll have your index here is 2 plus k over 2. Okay, so what we're going to do is we're going to attach it to one of these umbilic-free hemispheres. So again, an umbilic-free hemisphere in R3 will be a totally real Lagrangian hemisphere in TS2 with this transferring back through the normals. So this is here an umbilic-free hemisphere. Again, its Gauss map covers the hemisphere. And then we're going to join it up. Okay, so we're going to join to an umbilic free hemisphere. And then when we look at this, we can see, well, we're going to have umbilic points appearing in this, we're going to make it into a convex body. It's going to have umbilic points, and the umbilic points are going to have to add up to minus k over 2. Right? Because your total, there's no umbilic points here, and you want the sum to be 2, right? Because of the Euler characteristic. Okay, so you're going to have umbilic points here. Generically, you're going to have, they're all going to be negative index. Well, generically, they're going to be the lowest negative index. In fact, generically, they're minus a half. So you're going to have k minus a half in it. So you can perturb it under a generic perturbation, and you can, if there's some that are higher index and lower index, you can cancel them, and eventually you'll just get them down to the generic situation, which are these what are called hyperbolic umbilic points. So join to with an annulus with k umbilic points, of index minus a half. Okay, and then they will add up to 2. So that's what you're going to have if you attach it to something without umbilic points. Okay, these are called hyperbolic umbilic points. So these are called hyperbolic. If it was +1, they're called elliptic. This is an old phrase, old nomenclature for these types of umbilic points. So you have a hyperbolic umbilic point. Okay, so what we're going to do is, well, if you transfer that whole thing, it's very simple. It's not. What you're going to end up in TS2, or in the space of oriented lines, is you're going to end up with something that's going to have index 4 plus k. You're going to have your, this is going to be your Lagrangian totally real hemisphere. Again, all of these geometric transformation will translate over into this hemisphere. And here in this annulus, we're going to have these umbilic points, and these are complex points. So these are going to be complex points of index minus 1. Just multiplying by 2, nothing really too much there. Okay, and what we do in TS2 is I want to kill those minus 1 umbilic points. Okay, and the way that I kill those umbilic points is I connect some with OP2. So this is the geometric construction that goes from, again, in this 4 manifold, it will go from, so each hyperbolic complex point can be cancelled by connect sum with cross cap sum with or P2. Now I could give you the explicit construction. It is quite a constructive thing. You can just write down the Taylor series. You can then show how you can attach it, and you can show how. One way I can kind of motivate it is from what's called the Lie formula. So the Lie formula says that the total number of complex points on the surface is the Euler number of its tangent bundle plus the Euler number of its normal bundle. Now, if you take your surface and you connect some with an RP2, let's call that sigma prime, then the Euler characteristic is going to go down by 1. It's the Euler characteristic of the original minus 1. But what's interesting is actually the normal goes up by 2. The Euler characteristic of the normal bundle in this from this connected sum, or P2, I should say, that's all P2, is the Euler characteristic of the normal bundle plus 2. So overall, your index is going to go up by 1. I prime is I plus 1, and that kills the umbilic point. Okay, so you get these cross caps. So each one of these, you kind of put in a kind of a cross cap. I actually have some nice pictures of them. Unfortunately, I can't put the two together, the video and the thing, but we attached the RP2. So what we end up with is a closed surface. It's no longer a sphere. It's a sphere with K cross caps, but it's a closed surface, and it has a single umbilic point or single complex point. Actually, we're doing this all in TS2, so I should really just call them complex points. These cross caps are not Lagrangian, as it turns out. These cross caps are kind of twisting in R3, so they're harder to see in R3. I have some nice pictures of examples of them. You can see them quite easily, but they're not adding something. They're not doing anything to the surface in R3. Right? It's the lines that you're adding onto this surface, right? In TS2. Okay, so if we have this new surface, which was this one over here, connect some K times with RP2. What can we say about this surface? It will have killed all of these hyperbolic umbilic points. Now, this wouldn't work if these were of anything other than -1, right? This is the sidedness of this inequality that we have for the index. Is a kind of topological thing to do with RP2 being the lowest genus you can get to. Right? Otherwise, you could cancel other ones and you could say that's not happening either. So this here is a closed surface with a single complex point. And not only that, but it contains a Lagrangian hemisphere. So in other words, this is Fredholm regular. So therefore, you shouldn't be able to attach holomorphic disks to it. But it has a Lagrangian totally real hemisphere in it, so you can, of course, attach by our theorem using mean curvature flow, the theorem B. So this surface is a closed surface with a single complex point, and so the Riemann-Hilbert problem again, all of this argument we just did earlier, now in the global case actually works again. So the Riemann-Hilbert problem is Fredholm regular. Fredholm regular. And so you shouldn't be able to attach any holomorphic disks unless there's a complex point in the boundary around which you're wrapping your complex disk. But that's not the case because, again, you have a totally real Lagrangian hemisphere here, and you can always attach holomorphic disks to such a thing. Okay, so again, by A and B, so theorem A and B, theorems A and B, it's impossible. That's a contradiction now that we've got between these. So this is an impossible object to have created, so you can't have started out with the surface with those with that. Okay, so again, we're hearing, so we get contradiction. Okay, and no such complex point exists.
One question, this RP2, when you add this, do you stay in this space L?
Yeah.
When you add sort of this RP2, sort of connect it some with this RP2,
Yeah.
can you guarantee that you are still in this space L?
Oh yeah, absolutely. So in fact, yeah, I can. You have the down, but yes, the picture is as follows. Essentially, okay. So what is a hyperbolic point? So we had a question about what do these hyperbolic points look like? Well, hyperbolic points generally kind of look like this. They kind of have. That's an index -1. That's a surface with index -1. Okay, so what you do is you look at the normal line. So again, I'll bend that a little bit just so I can try and draw something that's off it. So you have your umbilic point here, and then you have your 3 directions, and you have this. And then you look at your normal lines. So you look at the normal lines on a circle around this. And then what you do, these are all the normal lines around that. And so then what you do is you go inwards, and what happens is it double covers the circle. So you can actually see the lines just coming in and double covering the circle. So it comes in, and if you like, the curve is like that, and then it kind of pushes over itself, and it ends up double covering a cylinder, in fact, a cylinder of lines. So you end up, you can really see it in R3. I mean, it's not a surface in R3, it's the set of lines that we're talking about. This RP2 really lives in the space of oriented lines. That's where it lies. But in R3, you can see it as families of lines and how they cross over each other. And then as you go in across this cross cap, it double covers, and you get this. Yeah, you get a cross cap of lines have been added to that surface.
And you can't go back to the from this world back to the original R3. There's no surface which would have.
No, these are twisting. Yeah.
This is no longer.
These are twisting. Yeah. So these are twisting. So this is one of the things that we found is in trying to attack the problem in R3, you always end up in this bigger space. The geometry faithfully represents it. That's not an issue. It has this bizarre signature, and you have to deal with that. And there are aspects of, in particular, theorem A that I mentioned earlier. You choose mean curvature flow in that space, which has all of its own problems. However, it's a proof from TS2. It's a property really of the space of oriented lines, and you can kind of see why that's the case. Because if you take a surface and you look at its oriented normal lines, and you push out to a parallel surface, an umbilic point moves to an umbilic point, and a non-umbilic point moves to a non-umbilic point. So really, being umbilic is a property of the way the normals sit. It's not a property of the individual surface. You actually have a whole one-parameter family. Right? So that's one of the reasons why this works, because umbilic points really live in the space of oriented lines. It's these complex points in the space of oriented lines that, that are, in fact, the key property that umbilic points have, that allow you to transfer everything over there, right? Is that fact. Moving out to parallel surfaces doesn't change this structure of whether it's umbilic or not. But yeah. So in fact, that's it. So the index, because it can't exist, you can't have an index 4 plus k, and therefore going back, you can't have 2 plus k over 2. Okay, so I'll leave it there. Thank you.
Thank you very much, Brendan, for the very nice talk. Maybe we've time for one question.
So I've got maybe a comment.
Yeah.
You were talking about geometry in signature 2,2.
Yeah.
There's a whole industry of people doing anti-de Sitter geometry, which is exactly doing that. I think they're asking different questions from the ones you're asking, but that is certainly a direction.
Is anti-de Sitter not hyperbolic?
So anti-de Sitter has got it's 2n minus
n
minus 2, comma 2.
Oh, okay.
The geometry there. Okay. And so this is.
It does turn up that one. Yeah, I guess relativity has meant that everybody looks at the Lorentz signature. But there are situations. Okay, anti-de-Sitter. Also, if you look at the ultra-hyperbolic equation arises when you do CAT scans. So in fact, it does appear in the real world in different situations. Yeah.
So just a comment.
Okay, thank you.
Let's thank Brendan again.